Drop a steel nail into water, and it sinks. Instantly. No drama, no hesitation. Straight to the bottom. Now take 200,000 tons of the same steel. Shape it, weld it, add engines, fuel, thousands of containers, and a crew. And somehow, it floats. That should be impossible. If a 5-gram nail can't float, how does a steel city the size of 4 football fields stay on top of the water? The short answer is surprisingly simple. A ship floats because of its shape. But that answer just opens up better questions. How can water, the stuff you swim through, hold up hundreds of thousands of tons? And what exactly changes on the day a ship sinks? In the next few minutes, you'll understand all of it, in plain language, and by the end, you'll know the one question the ocean asks every single object before deciding whether it floats or sinks. Put anything in water, and it shoves some water out of the way. That's called displacement. But water doesn't just politely move aside. It pushes back. You've felt this. Try holding an empty bottle underwater. It fights you. Let go, and it leaps back to the surface like it's late for something. That upward shove is called buoyancy. More than 2,000 years ago, a Greek scientist named Archimedes worked out the exact rule. In his bathtub. The story goes he was so excited he jumped out and ran through the streets shouting, "Eureka!" completely forgetting his towel. Here's what he realized. The upward force on an object equals the weight of the water it pushes aside. Push aside a little water, get a little support. Push aside a lot of water, get a lot of support. The ocean is basically a giant weighing machine. And it never lies. So, why does anything float at all? 2 forces are fighting. Gravity pulls the object down. Water pushes it up. When you place an object on water, it starts to sink. And as it sinks, it pushes aside more and more water. And the more water it displaces, the harder the water pushes back. At some point, if the object is lucky, the upward push grows equal to the object's weight. The 2 forces balance. The sinking stops. That is floating. Not magic, not stillness. A perfectly balanced tug-of-war that never ends. Back to our nail. The nail is small and dense, so even when it's fully underwater, the water it pushes aside is tiny and weighs much less than the nail itself. The upward push maxes out, and it's nowhere near enough. Gravity wins. The nail sinks. Every time. But now, take that same steel and hammer it into a thin, hollow bowl. Suddenly, it floats. The steel didn't get lighter. It got bigger. The bowl takes up far more space, so before it can go under, it pushes aside far more water. And now the water it displaces weighs more than the steel. Same metal. Same weight. Different shape. Completely different fate. And a ship? A ship is exactly this trick. Scaled up to something absurd. A colossal steel bowl, longer than 4 football fields, filled mostly with air. To pull this off at full size, shipbuilders start with a skeleton. A massive steel spine, the keel, runs along the bottom, with steel ribs curving up from it, like the rib cage of an enormous whale. Onto that skeleton, workers weld thick steel plates, sealing every joint, until the whole thing becomes one giant watertight shell. That shell is the hull. And here's the part most people never think about. Inside, a ship is mostly empty space. Engine rooms, cargo holds, corridors, all of it full of air. That emptiness isn't wasted space. That emptiness is the flotation device. Watch what happens when the ship is loaded. A crane lowers containers on board, and with every container, the ship settles a little deeper, pushing aside a little more water, earning a little more lift. The ship automatically takes exactly as much support as it needs, but there's a limit. And it's literally painted on the side of the ship. A set of marks called the load line shows how deep the ship may safely sit. Load past that line, and you're gambling with physics. One more piece of design genius. Inside the hull, watertight steel walls slice the ship into separate compartments, like a giant ice cube tray. Why does that matter? Because of what happens next. A ship stays up only while it keeps enough water pushed aside, which means keeping the water out and the air in. If the hull is torn open, water pours in and starts replacing that precious air. The ship gets heavier and settles deeper, which lets in more water. It's a vicious cycle, and loose water inside a ship is even nastier than it sounds. As it sloshes from side to side, it can rock the ship harder and harder until the ship leans and capsizes. This is exactly what those compartments are for. Seal the doors, and the flood stays trapped in one cube of the ice cube tray. The rest keep their air and keep the ship afloat. Which brings us to the most famous ship in history. The Titanic was called practically unsinkable, and to be fair, the design was impressive. 16 watertight compartments, built to stay afloat even with the 4 front ones flooded. The iceberg opened at least 5. Worse, the compartment walls didn't reach all the way to the top. As the bow dipped lower, water simply spilled over each wall into the next compartment, like tilting an ice cube tray under a running tap. Compartment by compartment, air was replaced by water, until the hull could no longer push aside enough water to carry the weight. Buoyancy lost the battle. Modern ships are designed by the lessons of that night. Taller walls, smarter compartments, and strict rules about how much damage a ship must be able to survive. So, if flooding sinks a ship, could you flood one carefully and sink it on purpose? Congratulations, you've just invented the submarine. A submarine doesn't use different physics. It just treats buoyancy as a control knob. To dive, it opens special ballast tanks and lets seawater flood in, replacing air, exactly like a sinking ship, except entirely on purpose. To rise, it blasts that water back out with compressed air, and buoyancy takes over again. And with the right balance, it can hover, perfectly suspended at a chosen depth, like a steel fish. Engineers call that neutral buoyancy. A submarine, in other words, is a ship that turned sinking into a feature, not a disaster. So, why does a nail sink while a gigantic steel ship floats? The nail is small and solid. It's fully underwater before it can push aside enough water to matter. The ship is enormous and hollow. It shoves aside a huge amount of water, while most of the ship still rides above the surface. Shape, enclosed air, displaced water. That's the whole secret. And here's the part worth remembering. The ocean doesn't care what you're made of. Steel, wood, even concrete. It makes no difference. The ocean asks every object just one question. How much water have you moved? Answer well, you float. Answer badly, you sink. If you liked this video, hit the like button. And if you like the kind of content we make, subscribe. And tell us in the comments what you'd like us to explain next.